Hello everyone, welcome back. This is Programming and Optimization with Intel Architecture, the hands-on workshop series. And I'm Andrei Vladimirov. As usual, I will do a quick 2-minute overview of the course material for those who have just joined us. This is a course. Um, this course consists of 10 sessions, and today we are in session number 3. Earlier in the course, we talked about uh, Intel parallel architecture and focused on Intel Xeon processors and Intel Xeon Phi coprocessors. We also discussed programming models for Xeon Phi, native programming and offload programming. And starting from today, the discussion will switch to parallelism, and we will talk about vectorization. So starting from today, the discussion will be completely generic. It is not tied specifically to Xeon or to Xeon Phi, but we will be using Intel software development tools. And in principle, what we talk about applies to a variety of processors with multiple cores and vector units. Um, in addition, even though we are going to only discuss C and C++ examples, the principles apply also to Fortran and possibly to other languages. So this course has a web page, and the web page is colfaxresearch.com how1509. This is where you can obtain the slides of my presentations and also view recordings of earlier sessions. So this is the page. If you scroll down, you will see recordings of session number 1, session number 2, and today's session number 3, so you can download slides and the zip file right here. If you have a hard time navigating to this page, you can go to your email, and the reminder that you received this morning looks like this. Reminder starts, this session starts in 1 hour, now contains this URL. So you can just click from your email, or you can go to colfaxresearch.com and navigate from the main menu, training, web-based. So it's right here. This course is based on our original book, Parallel Programming and Optimization with Intel Xeon Phi coprocessors. It contains discussions of all the topics that we talk about in the workshop and more. And the book is available at xeonphi.com/book. This is also the source for all the exercises that we are dealing with. This is a hands-on workshop, so we are providing remote access to training servers to a number of people. And if you have received your remote access, great, you will be able to use it in the second hour. If not, then you must be on the wait list, and the earlier you registered, and as long as you attend the live broadcasts, the wait list will trickle down to you soon with a high probability. Attend 6 sessions out of 10, and you can get a certificate of accomplishment for this course in the fundamental level. And just visit us at colfaxresearch.com for more resources on parallel programming. Let me do a quick overview of the discussion in the previous 2 episodes. We are talking about Intel platforms, specifically Xeon processors, which are general purpose parallel processors, and Xeon Phi coprocessors, which is highly specialized parallel processors. And the common theme of this entire workshop is that code designed and optimized for one platform will run well on another, as long as you have enough parallelism and you are using memory efficiently. So today we will start talking about parallelism and focus on the vector processing capabilities both in Xeon and Xeon Phi. Earlier we also talked about how to run something on a Xeon Phi coprocessor, and we discussed 2 programming models: native programming, where the entire application runs on the coprocessor, and offload programming model, where you start the application on the host CPU and offload parts of it to the coprocessor. So if you missed those discussions, you are welcome to go to the course page and view the recordings for sessions 1 and 2. A hello world application might look like this. It gives no hints that it knows anything about Xeon Phi, but when you compile it, you have to compile it with the argument -MMIC. And then, because Xeon Phi acts as an independent compute node, you have to copy this executable to Xeon Phi and run it from the Xeon Phi coprocessor, or you can use MPI for scaling across a cluster. Offload programming might look like that. In this case, it is clear from the code that the application is designed for Xeon Phi because you have directives like pragma offload target mic. And this pragma says that at runtime, here you need to, here the program will communicate to the driver, send to the driver this code compiled for the Xeon Phi architecture and execute there. And then the control will return back to the host. So the discussions in the first two sessions were essentially about how to run something on a Xeon Phi coprocessor without concern for parallelism or performance. Today we are starting to talk about performance. Excuse me, I said it wrong. Today we are starting to talk about parallelism, but we will not really be concerned with performance. We just want to learn how to express parallelism on two levels. And we will begin with data parallelism, in other words, vectorization. When I say vectorization, in the context of Intel architecture, this is synonymous with SIMD. And let me explain where it stands on the level of the architecture. For both Xeon processors and Xeon Phi coprocessors, and actually for other Intel parallel processors such as Intel Core, you can think of them as symmetric multiprocessors, which means that you have multiple cores. On Xeon, this will be up to 18 cores per socket. On Xeon Phi, this will be up to 61 cores per socket in the first generation. And all of these cores share the memory address space. Cores can run independent processes or independent threads, and we will talk about threads on Monday in the next session. So software threads can be distributed across cores, but even more, each core represents itself as 2 or 4 logical processors. So effectively, you can put up to 2 threads, up to 2 software threads on each physical core, and up to 4 threads on each physical core on Xeon Phi. These logical processors have some of the resources replicated, but they share other resources. One of the resources that they share is a vector processing unit, and this is where performance is. So you can see that there's, well, I drew multiple slots in this vector unit representing parallelism inside of it, but you can see that there's parallelism on 2 levels. There's multiple cores, and there are multiple vector lanes inside of every core. So what does that mean? Different cores are different processors. They can run independent streams of instructions. These are very different from, say, a GPU core, because in a GPU, all cores go in lockstep and they apply the same operations at the same time. In Intel architecture, this is very different. Each core is independent of every other core. They are only talking to each other through the shared memory and through the shared caches, and caches are kept coherent across the different cores by hardware. So this is one level of parallelism. Different cores can run different streams of instructions. Now, today we are going to focus on another level of parallelism. Within each core, there is a vector processing unit, which is a SIMD device. SIMD stands for single instruction multiple data. A vector unit can take multiple numbers, integers or floating point numbers, and apply the same operation to these numbers as one instruction. Effectively, that means that if your application is capable of using vectorization, then you can process as many numbers as the vector unit fits in the same amount of time as you would normally process one number. But the catch is that different vector lanes, all of the vector lanes essentially run the same program. They run the same instruction in every clock cycle. So there is, you can say that the different vector lanes have less flexibility than different cores because, well, you can distribute different data elements across cores and apply the same instruction. But you can also distribute different programs across cores. Vector lanes are, unlike cores, going to run only one instruction on multiple data elements. To illustrate what's happening, I want to show you these two pseudocodes. So don't treat this as a code in Fortran or C. This is pseudocode explaining what's going to happen when you use vectorization. Suppose I'm adding two arrays together, A and B, and each array has n numbers where n is in the hundreds or in the thousands. If I do this addition one element at a time, I would call it a scalar calculation. But if I have a vector processor, such as an Intel Xeon or Intel Xeon Phi, then I can potentially take up to 16 numbers or however many numbers the vector unit fits and add 16 elements at a time and write back the results. So this is potentially a huge speed up. The number 16 is specific to the Xeon Phi architecture, and specifically it applies to single precision calculations or to calculations on 32-bit integers. If I'm dealing with double precision, then instead of 16, I will be able to fit 8 numbers in the vector register. If I'm dealing with a Xeon processor, then the width of the vector register is half of that. This table should explain what is happening. And this table summarizes vector instruction sets available in Intel processors. So vectorization was a big deal in the 1970s with Cray computers. And when personal computers first appeared, vectorization was not a word. So if you started learning programming in the early 1990s, probably vectorization was never discussed. But starting from the late 1990s, Intel started adding instruction sets that are vector instruction sets to their Pentium and then later processors. And you can see that the width of vector registers was increasing, and also the variety of operations that you can do with vectors and the types of data that you can process with vectors were all evolving. Today, the latest generation of Intel Xeon processors supports instruction sets up to AVX2, which are 256-bit vectors. So with integers, you can fit 4 64-bit integers or 8 32-bit integers into a vector register and apply one operation to this many elements. With floating point numbers, you can fit 4 double precision floating point numbers or 8 single precision floating point numbers. With Xeon Phi of the first generation, the instruction set is called IMCI, or sometimes it's called Knight's Corner instructions. The vector register width is twice as long as on Xeon. So this is where the number 16 comes from. If you're doing single precision, then 512 divided by 32 bits in a number is 16 numbers. The second generation of Xeon Phi architecture will have a yet different instruction set called AVX 512. It is also going to be a 512-bit instruction set. This is a list of this is not a detailed list, but this is a summary of all the operations that you can do with vectors. You can load from memory into vectors contiguously or with a stride using gather and scatter. You can do normal arithmetic operations on numbers using vectors: addition, multiplication, subtraction, division. You can do vector comparison, vector type conversion, or you can use vectors to do bitwise instructions on 512 bits at a time. Also, some essentially serial operations such as reduction across vector lanes is available in Xeon Phi, and Xeon Phi also supports masked vector instructions where you apply the operation to some numbers but preserve other numbers on other vector lanes on output. How do you use vectorization in your code? There's two approaches. One is to explicitly call vector instructions, and the other is to rely on the compiler to vectorize the code for you, so automatic vectorization. We advocate the latter. We really think that automatic vectorization is the way to go if you want to make your code portable across different architectures and also future-proof. But before I go there, I want to illustrate the alternative, explicit vectorization, and it can be done with assembly or with intrinsics. I like intrinsics, which are special functions that give you access to processor instructions. So back again to adding vectors a and b. If you have a loop like this, this is a scalar loop. You could potentially rewrite this loop so that you stride through it with a stride of 16. And for every addition, you would have to run 4 instructions like that. This instruction loads data from memory into a vector register, AVEC. This instruction loads data for vector b from memory into the vector register. Then this third operation is actually the vector addition. So this is where I add 16 values in vector A to 16 values in vector B. And then I have to store the result back in memory from the vector register to memory. And this code, you can see that, well, this is many lines of code. Also, it has these prefixes that are specific to the Xeon Phi architecture. So if I tried to compile this code for the Xeon, it wouldn't compile. So if I have parts of my application expressed with intrinsics, well, I will have to write this code once for every architecture on which I'm compiling. Also, this code assumes a lot of things about vectors, about arrays A and B, and about the value n. Specifically, it assumes that n is a multiple of 16. If n is not a multiple of 16, then I would have to have a tail loop. I'm sorry, I would have to have a remainder loop after this loop. Also, this code assumes that arrays A and B begin on an aligned boundary. They begin on a multiple of 64 bytes. Otherwise, these load instructions are not going to work. If this is not the case, I would have to implement a peel loop and perform a few operations with scalars. We will talk about this later in this course. But what I'm saying is that going from a code like this to a code like that, which is vectorized, is not a trivial task. And if you do it by hand, you have to do it for every architecture. The compiler, fortunately, Intel compilers fortunately support automatic vectorization. And it is a very powerful feature. Today, I will, in the slides, I will demonstrate only examples of vectorization, of automatic vectorization of primitive code. But in the hands-on part, we will see that the compiler is capable of vectorizing really tricky situations. So this is a sample program that you can actually copy-paste and run. It has 2 arrays, it initializes these arrays, and then it does my favorite operation a plus b and prints out the result. So this is the loop of interest. This is where we can potentially use vectorization. In fact, we can use vectorization here as well, but let's focus on the math because it represents what most of us are doing in our daily life. When I compile this code with the Intel compiler, by default, without setting any flags, the compiler will try to vectorize it. But I can get diagnostic information on what happened by using these 2 compiler arguments Well, just one is enough actually. qopt report. This compiler argument makes the compiler produce a file called autovec.opt. Autovec corresponds to the source file name, and this text file contains information about vectorization. The second argument that I'm using, qopt report phase vec, is only needed if you want to clean up the report and only print information related to specifically vectorization. So this is optional. The one that you really need is qopt report. Notice that if you were working with an older version of Intel compilers before, they used to have an argument vec report. That argument was deprecated. Now we have to use qopt report. So this text file will contain statements like this, and the way to read these statements is focus on what's in parentheses. So autovec.cc is the source file name, and then I have 14. 14 is the line number. So this is the line number 14 in my code, and this piece of report applies to this line. 3 is actually the column because, well, I have an offset of 3 characters. And the compiler says vectorization support, unroll factor set to 2, that's not important, but that's what's important. Loop was vectorized. So loop was vectorized in all caps is a good sign. It means that at least the initial attempt of vectorization has succeeded, and the loop is actually executed with vector instructions. We will talk some more about what to do when it is not vectorized, and also in session number 6 we will talk about optimization, because loop was vectorized is a good start, but to make vectorization efficient, sometimes you have to take additional measures, such as choosing good data structures, aligning data, and giving compiler hints that allow it to drop unnecessary work. Now, as promised, this is a this is an example that illustrates that the same code we can compile both for the Xeon architecture and for the Xeon Phi architecture. Let's go through this command line. I'm calling the Intel C++ compiler, compiling this source file, and I'm using the argument xhost. The argument xhost tells the compiler that you want to target the processor architecture on which you are compiling. Well, this is a very common use case for developers of scientific applications. You are compiling on the same computer on which you're going to run. If you are targeting a different architecture, then instead of host, you can plug in the name of the instruction set, such as AVX2. Then I request the optimization report, and I get loop was vectorized. Notice that in the previous example, I did not use this argument. And sometimes the Intel compiler will be shy. It will not implement the latest and greatest vector instructions. Instead, it will implement legacy instructions, which allow your code to run on older processors, but they do not use your processor efficiently. So this is a very important argument. And as you can see, the loop was vectorized. I get the correct results. If I want to compile the same code for the Xeon Phi architecture, instead of xhost, I will use -mmIC. And now I'm going to switch to the next slide and try to spot the difference. So the difference is now that I'm using -mmIC, and this uses vector instructions for the Xeon Phi architecture. Of course, when I run the code, well, I have to either copy it to the Xeon Phi coprocessor or use MIC native loadx, as we discussed in session 1. But the same procedure, I just recompile the code, and the compiler implemented different and the compiler produces different vector instructions. Let me go back a couple of slides and explain exactly what happened when the compiler vectorized this loop. The compiler essentially represented this loop as a set of iterations of length 16. Well, for the Xeon Phi architecture, it split this loop into chunks of 16 iterations, and in each iteration it loads 16 values of A, 16 values of B from memory into vector registers, does the addition, and stores the results back. But the compiler also takes care of all the situations that can occur at runtime. For example, if n is not a multiple of 16, the compiler will take care of that because it will automatically implement a remainder loop. What if the beginning of array A and B, or maybe array A but not B, misses an aligned boundary? What if A begins on a non-aligned boundary and B begins on an aligned boundary? The compiler can take care of this. If both begin on the same offset from an aligned boundary, the compiler will implement a peel loop. If they have different offsets, the compiler will probably take care of that by reading two cache lines and then combining them. Basically, it can handle a variety of situations with regards to alignment and the number n. This makes the code general. As we will see later, sometimes this is not optimal, but the code will work. I showed you an example of automatic vectorization of A plus B. Well, A plus B is not a big deal, even though the compiler takes care of a lot of situations that you really don't want to think about as a programmer. But automatically vectorized loops do not have to be simple. They may be quite complex. I will show you in session number 5 an n-body simulation where the compiler vectorizes a loop like that. See, I have a loop in variable I, and this variable I is the index in array particles, in arrays particle x, particle y, particle z. And also I have another array which has the index j. So with respect to vectorization, this is a constant. Right? The compiler will take this loop, it will transform it in loops of 16 iterations, and this will become a constant across all vector lanes. And then the compiler can take an expression like that. So this will be a vector, this will be a vector, this will be a vector. It will do multiplications and additions. It will actually recognize opportunities for fuse, multiply, add. It will add this constant, which will become a vector of constants. It will call a transcendental function on vectors and do a lot of processing down the line. So automatically vectorized loops can be complex, and trying to implement this with intrinsics, you're risking to have complex code which is not future portable and not portable across different architectures. Plus, you have to, well, you will not be, it will be very difficult to take care of all the situations with regards to the loop length not being equal to the vector length and different alignment situations. The compiler vectorizes only 4 loops, and these 4 loops have to be countable. A countable for loop means that you know the number of iterations once you begin the loop, or even when you are compiling the loop. If you have a funny for loop where the upper bound is modified from iteration to iteration, this is not really a for loop, this is a while loop, and such a loop should not be automatically vectorized. Also, the default behavior is that the compiler targets the innermost loop for vectorization. So if you have nested loops, you can expect that the compiler will target the innermost loop, even though you can sometimes override this behavior. I will show how. And the compiler will vectorize loops with complex memory access patterns, such as strided access pattern. But it will not vectorize loops with indirect memory accesses. For example, if you have A of B of I, and I is the loop index, this is not going to vectorize. And the compiler will not try to vectorize, in some cases, when you have irregular memory access pattern, where you have vector dependence. I will discuss it in a second. While loops cannot be vectorized, for loops with funny upper bounds. Outer loops cannot be vectorized unless you use this special hint. And loops with complex branches also cannot be vectorized. But loops with simple branches actually can be vectorized, and we will see it. So what I've discussed so far is automatic vectorization of loops. And at this point, I want to make a quick pause and see if there are any questions. By the way, if you have any questions, look for a box in your interface called questions. This box allows you to type a question, and if this question is um, relevant to the discussion right now, I will try to address it immediately. If not, I will address it either later or online. There is also an option to raise hand in your interface. I advise you not to use this option and to use the questions instead. All right, so let me go to another topic on automatic vectorization. And I've talked about how loops can be vectorized, but there is another way to request vectorization from the compiler, and this is array notation. Array notation is something that is familiar to Fortran programmers. Fortran programmers have had it for a while. In C, array notation is not a part of the language, but Intel compilers support language extensions that allow you to use array notation. So you may have expressions like this: A0 colon 16 plus equals B32 colon 16. So Fortran programmers will recognize this notation, but I want to warn Fortran programmers that the syntax in C is slightly different. So the syntax is this: A0 colon 16 means that I want to apply some operation to 16 numbers starting from 0. For array B, I want to take 16 numbers starting from 32. So the first number is the start, the second number is the count. In Fortran, this is different because in Fortran you indicate start and end rather than start and count. So this kind of an expression will vectorize, and this is a shorthand for writing a loop. So functionally, there is no difference between doing that and writing a loop. But there is a case where array notation is more powerful than automatic vectorization. And this case is when you have strides, especially different strides in the left-hand side and in the right-hand side. So strides you can indicate as this third argument in this array. And this expression means the following. I want to take 16 elements in array A, starting from element 0 with a stride of 2. So I want to take elements 0, 2, 4, 6, and so on. This means that I want to take 16 elements starting from 32 with a stride of 4. So I will take elements 32, 36, 40, 44, and so on. The compiler is able to better see the the memory access pattern in such an expression than if you were to write this with a loop. And we actually have a paper. You can click here and get the paper, which uses array notation in exactly that case. And we did see that array notation outperforms loops in this specific case. With multi-dimensional arrays, you can still use array notation, just add the second index. And also, if the compiler knows the dimensions of arrays, you don't have to specify the loop bounds. You can just put a colon. It means the entire array. This is a code snippet from that paper. This paper computes, takes a different approach on parallelizing one-dimensional large fast Fourier transforms. And you can see that we are using the Cooley-Taki algorithm, which essentially requires you to take every other element in an array, and this will become and this pattern. So in the right hand side you have a stride of 2, in the left hand side you have a stride of 1. You can see that in the left hand side we can have stride of 1, in the right hand side stride of 2. We can also use negative strides, and this is much more compact than a loop. Plus, it vectorizes better because the compiler is better able to recognize the memory access pattern. There is yet a third way to request automatic vectorization from the compiler, and that is SIMD-enabled functions. So consider this case. I have a function that does my favorite operation a plus b. Well, in this case, this function takes x1 and x2 and returns x1 plus x2. Suppose I want to use this function in a loop, where I call this function on elements of two arrays. So I'm back to doing my favorite a plus b, but I'm calling this as a function. Of course, I wouldn't normally implement a function for something as simple as this, but you will be able to see later that SIMD-enabled functions can be complex. So pretend that there is something heavy going on in this function. If I do this, and the compiler sees the body of this function in the same source file, then it will inline this function, and we are back to just loops with arithmetics. But let's think of a situation where this function is in a separate source file from that loop. This can and does occur in reality when you are dealing with libraries. Suppose this is a library function. You are writing a library with, for example, special math functions, and then you are linking this library from the user application. And actually, the author of this function and the author of that loop may be different people. Even more, the source of this function may not be available to the developer of the loop that uses it. The compiler will normally refuse to vectorize loops like that. It will say that function is not a candidate for vectorization, but there is a way to inform the compiler of vectorization opportunities and still have this loop vectorized. So this can be done through SIMD-enabled functions. To make a function SIMD-enabled, you have to warn the compiler when you are building the library that this function may be used in a data parallel context. You can do it using an Intel proprietary syntax attribute vector, or I will show later cross-platform standard in OpenMP4 for doing the same. This attribute vector tells the function that it may be used in a data parallel context. So the compiler will compile not one version of this function, but several. It will compile a version where the function actually takes two scalar arguments and returns one scalar result. It will also compile an implementation where the function takes two short vectors as integers and returns a short vector as a result. In some cases, the compiler will also implement a case where the function takes two short vectors and a mask and returns a short vector, and it will mask out some of the vector lanes. This can be useful for loops with branches. When I'm using this function, normally I would have to put a hint, pragma SIMD, before this loop, and this hint tells the compiler that this function is not a simple function. It actually has vector implementations in the object file or in the library file. So the compiler should look for these vector implementations and try to vectorize the code. And if the compiler finds it, then the loop will be vectorized. And as I mentioned, SIMD-enabled functions can be declared with this Intel proprietary syntax, or if you want to be dealing with a cross-platform standard, you can use this syntax pragma omp declare SIMD. This is an alternative interface for the same backend. And the pragma hint corresponding to that is pragma omp SIMD. So these are all parts of the OpenMP 4.0 standard. This pragma tells the compiler that it has to compile this function several times, preparing for usage in a data parallel context. And that pragma tells the compiler that there is a special implementation in the library file, so it has to look for it. When you declare a function as SIMD-enabled, you can specify additional properties. For example, you can give the compiler hints on alignment of some of the arguments. You can tell the compiler whether or not you intend to use this function in a loop with branches. So it will prepare for masking or not prepare for masking. You can indicate a safe vector length um, such that it doesn't cause vector dependence. Sometimes some of the arrays, some of the arguments of your function will be floating point numbers, but others will be integers. And these integers may serve the role of indices. And between different vector lanes, there may be a predictable stride of these indices, and you can indicate this to the compiler. Sometimes you can indicate that you are doing reduction across multiple vector lanes into one of the arguments. Or some arguments may be uniform across different vector lanes. For example, think of the Bessel function. It has the order and the argument. So in principle, this is two function arguments, but normally in a data parallel context, you would call the Bessel function with the same order on different arguments. In this case, you can specify that the order is a uniform argument across different vector lanes. By the way, when you use pragma OMP declare and pragma OMP SIMD, you have to compile the code with the argument QOpenMP to link the OpenMP library. We will talk about OpenMP tomorrow. Not tomorrow, excuse me, on Monday in session number 4. So SIMD-enabled functions look like regular C, C++ functions operating on scalar numbers with scalar syntax, but they can be used in data parallel and thread parallel context, and you can expect automatic vectorization and actually even parallelism across multiple threads. The restriction is that every SIMD-enabled function must not modify any data outside of itself. In other words, it has to be pure. You cannot modify global variables in a SIMD-enabled function. For an example of usage, you can refer to this paper. I actually have a code snippet from this paper. It illustrates that SIMD-enabled functions may be complex in the sense complicated. Obviously, they can operate on complex numbers, but they can also be pretty involved. Like this function is implementing an analytic approximation of the error function. So it takes one scalar argument, returns one scalar argument, but I declare it as SIMD enabled. And see what happens to this argument. I take the absolute value, and then I declare a constant, which becomes a constant of vectors. And then I have this complex expression on these two null vectors. I'm using transcendental functions, and I expect them to be vectorized. I'm actually computing a polynomial with my vector and returning the result. So all of that, each of these elements will, each of these instructions will run in every vector lane of my vector. This is how vectorization is going to work. So there are three ways to express vectorization opportunities to the compiler: loops, array notation, and SIMD-enabled functions. Ideally, you would expect that once you've expressed vectorization opportunities, the compiler will just vectorize. But what do you do if vectorization fails even though it should have happened? So let's talk about this a little bit. First, let me talk about true vector dependence. I was saying all the time that yes, loops can be vectorized, but not every loop can be vectorized. It is only safe to vectorize a loop where you have data parallelism, meaning that you can compute different iterations in this loop independently from each other, even if these iterations are very close to each other. But sometimes you have vector dependence. This is an example of a loop with vector dependence. I have two pointer-based arrays, and what I'm doing is I'm setting a of I equal to, well, b of I, but then I'm using a of I minus 1. So this is vector dependence, before I can compute A1, I have to know A0. Before I can compute A2, I have to know A1. So there is no way that I can run these operations in parallel. I will just produce incorrect results. So this loop cannot be vectorized, and the compiler will actually say that it did not vectorize this loop, which is the correct behavior. But now let's look at something that seems to be straightforward to vectorize, but the compiler will for some reason complain. I have a function, my copy, where I copy A into B, and this assignment is, well, potentially vectorizable. You can load 16 values of B and store them in 16 values of A. But when I compile this loop, the optimization report will say loop was not vectorized, non-vectorizable loop instance from multi-versioning. What does that mean? It means that the compiler suspects vector dependence, and that's why. To me, as the designer of this function, it seems straightforward that A is one array and B is another array. But somebody who uses this function may be smarter than me, and they might feed into the function A, which is offset from B by one element. So essentially, I will have A of I equals to A of I minus 1, if B equals A minus 1. So the correct way, in this case, to run this loop would be to run it element by element. I will take A0 and I will propagate it across all the other elements in A. But it would be incorrect to try to take 16 values of B and copy them into 16 values of A, because they are actually pointing to overlapping memory regions. So there is a lot of terminology to learn in this context. One term is assumed vector dependence. This is what's happening, why the compiler is refusing to vectorize the loop. Another term to learn here is pointer aliasing. If somebody feeds B equal to A minus 1, then these pointers are said to be aliased. In other words, they are pointing to parts of the same memory region. To deal with this situation, what we have to do is pointer disambiguation. Here's one more term for you. Meaning we have to tell the compiler that the intended usage of this function is such that these pointers are not aliased. They are pointing to different memory regions. And one of the standard ways to do this is to include pragma ivdep, this compiler hint. Ivdep stands for ignore vector dependence, and it tells the compiler that pointers are not aliased. It does pointer disambiguation. In this case, when we compile the loop, we will see multi-versioned version 2. Loop was vectorized. Pragma ivdep, the need for it has been known for a while. And this is a very strong statement. You are promising to the compiler that there is no vector dependence. Sometimes you cannot make a promise that general, but you will know that some pointers are not aliased with other pointers. In this case, you can use a different language extension, the keyword restrict. This keyword you have to put after the declaration of a pointer variable, and you have to compile the code with argument -restrict. So when you compile the code, you will have -restrict here. And this will tell the compiler that while this pointer A lives, no other pointer is pointing to its data. This is a more fine-grained approach than pragma ivdep, because some pointers may be aliased, others may be not aliased, and you may want to only focus the compiler's attention on those that you know are going to be independent. We will talk about this situation in the hands-on part, and we will also talk about some of the other tuning knobs for vectorization. Some of them we will discuss today, others we will discuss in session number 6. This list contains clickable links. So when you download the slides, you can click any of these names. It will take you to the page in the compiler manual. And these are what I call tuning knobs for vectorization. Some of them we discussed, some others we will discuss later. Some actually you can refer, we will not discuss in the course, but you can refer to the manual or to our book for an explanation. Pragma-CMD tells the compiler, vectorize this loop. I don't care what your excuse is. This tells the compiler, vectorize the loop, even if you think that vectorization is inefficient. Pragma vector aligned tells the compiler, vectorize this loop and assume that all memory addresses are aligned on a good boundary, and do not implement peel loops. We will talk about in session 6. Assume aligned is a more fine-grained approach. It applies to just one pointer rather than entire loop. Pragma vector non-temporal tells the compiler that when you vectorize, I want you to write data into memory bypassing caches, because I'm not going to reuse this data. This is useful when you really are not going to reuse the data because it does not pollute your caches. Pragma no vector tells the compiler that you don't want to vectorize this loop. Pragma IV dep tells the compiler that pointers are not aliased in the entire loop, and it is safe to ignore any assumed vector dependencies. The restrictive qualifier achieves a similar result. Pragma loop count tells the compiler that you want to vectorize this loop, and at runtime you expect on average, or at least, or at most, this many iterations in the loop. It allows the compiler to choose an optimal optimization strategy. And I also have here 3 compiler arguments. QOptReport requests the vectorization report, and actually you can tune the verbosity of this report by including an integer, 1, 2, 3, 4, 5. The greater the integer, the more information you get in the vectorization report. Capital O followed by an integer is a control for optimization level for the compiler. So I want to point out that the default level of optimization O2 includes automatic vectorization, but level O1 does not include automatic vectorization. There is also compiler argument X. If X is followed by the word host, the compiler tunes vector instructions in the code to the same architecture on which you are compiling. But instead of host, you can include the name of the instruction set, and it will tune, the compiler will tune the code for a specific architecture. If you would like to see a more complex example on automatic vectorization, you can go to this paper. It discusses a physics-motivated example of binning particles. You have particles coming in, for example, from a cylindrical detector, and you want to bin their coordinates into counters on a Cartesian grid, and it explains how vectorization can be implemented here. We will have a similar example in session 6 of this course. So today, we talked about vectorization. Vectorization is another word for data parallelism, and it is available in each core. Automatic vectorization is a function of the compiler where it takes scalar loops or array notation or CMD-enabled functions and produces vectorized binary code. QOptReport is an argument that allows you to study what the compiler did, and you have options for complex situations to use CMD-enabled functions, array notations, and compiler hints. We talked about how to just express vectorization opportunities. We did not talk about performance. Performance we will discuss later in the course in session 6, and we will talk about alignment, data structures, vectorization pattern, and programming techniques such as strip mining for exposing automatic vectorization, and we will see more compiler hints. In the next session on Monday, we will talk about another level of parallelism with threads, and we will learn how to use multiple cores. So at this point, I will go back to the questions and see if there's questions that can be addressed globally. Yes, one interesting question here is, does the Xeon Phi suffer branch divergence problems like GPUs, i.e., if two threads enter different execution paths, as in if else statements, their execution is serialized. This is very interesting. I hope to illustrate what's happening in the hands-on part. And the situation is basically you have a loop and you have branches in these loops. With a SIMD machine like a Xeon Phi, you are actually in a better shape than with a GPU, because what will happen if you have branches inside the loop is the compiler will actually evaluate the code in both parts of the branch for all vector lanes, and then it will write back the result into memory depending on the value of the branch. So the compiler will do masking inside of a vector. So that's what's going to happen. Another question is how many vector registers are there per core? I believe there are 32 entries in the register file on Xeon Phi. I am not sure because as a programmer who likes to rely on automatic vectorization, I never had to worry specifically about the number of vector registers. The compiler takes care of that for you. It takes care of register renaming and about using as many vector registers as you have a need for in your code. So if you have any more questions, feel free to type them in. I propose that we take the usual 2-3 minute break, and actually now is 9:57, so let's assume at the top of the hour at 00 minutes, and we will begin the hands-on part. As usual, if you don't have remote access to our system, I highly recommend that you stay tuned because you will be able to follow along with me, and I think that that's a good way to learn. Also good news for people on the waitlist that right after this class, I will clean up the waitlist and remove the people who chose not to participate and reassign seats to people who are down the waitlist, hopefully more interested. So thanks. See you in 2 minutes in the hands-on part. Stay tuned. Welcome back. I am ready to start, and hopefully if you have remote access you have connected. If you don't have remote access, follow along. I think it will be fun. So today I'm going to labs, and then I'm going inside of chapter 3, which is expressing parallelism, and I will be dealing with this lab, 301 vectorization. By the way, if you have been provided remote access and you have technical issues connecting, I really want to resolve these issues, so feel free to respond to the email and I will help with any questions. So this time I have two files, vectorization.cc and worker.cc. I will start with vectorization.cc and let's see what's happening. So this exercise essentially teaches me how to deal with automatic vectorization. And in my code, I have a lot of code snippets that seem like good candidates for vectorization. So I have arrays A and B, and here I'm initializing them, and then surprise, surprise, I am adding A plus B. And then I have another loop that actually calls a function. You can tell by the name of this function that essentially I'm still doing A plus B, but this function is actually defined in a separate file. The separate file is called worker.cc, and this is where I have my scalar add. I also call a function, and inside of this function I have arrays A and B passed to me as pointers, and then I'm running a loop that can potentially be vectorized. So let's compile this function and see what happens. Oh, something happened to my display here. Um, something strange is happening, so I'll just use it differently. Or why don't I do this? Actually, this may help people who are using NX. See, yeah, I was trying to switch between this window and that window. And if I press Control Tab, as I usually do, it actually switches between windows on my host system. So I can go to System, Preferences, Keyboard Shortcuts, and then I will scroll down, I will scroll down, I will scroll down until I see move between windows. And here I will create a different shortcut. I like, for my keyboard it seems to work fine, Alt backwards apostrophe. Then I can press Alt backwards apostrophe to switch between windows. So let me do that. And I can now hide this and give you more room to see the code. Okay, so as promised, let me compile the code. And there is a make file that does the compilation for me. So I have to just type make. As you can see, I compiled vectorization.cc using the argument -x-host. So this is going to be compiled for the host architecture for my CPU. And then I requested the optimization report. And for convenience, I redirected the optimization report from the default file to this file, vectorization opt report. Then I did the same with the other file, worker.cc, and then I linked my application. After that, I did the same operations, but now compiling executables for the Xeon Phi architecture with the argument -mmic. So this is vectorization.cc compiled for Xeon Phi. This is worker.cc compiled for Xeon Phi. Then I'm linking them. And this time, to run my application, I have very convenient shortcuts. I can do make run dash CPU, and it will run the code on the CPU by just running app CPU. And I can type make run Mike, and it will do all of the magic that's required to run the code on Xeon Phi. It will copy the executable to Xeon Phi, SSH there, set up all the library paths that I need, and then execute the application. When I execute this application, in fact, nothing exciting happens. Let me do this again. When I run on the host, it just runs and no output. Well, not surprising because I don't have any output in the application. What I wanted to focus on is actually the vectorization report. So let me open in a separate window vectorization opt report. So this is the vectorization report that the compiler produced for the host architecture. And let me study it. First, it says that loop beginning in line 28 was vectorized. And this is the loop where I initialize matrix A. Actually, it doesn't say anything about that because I know from experience it actually fused this loop with that loop. Then it says that loop in line 32 was vectorized. That's good news. My favorite A plus B is vectorizable. But then, scrolling down, I find that in line 36, the loop was not vectorized because loop with a function call is not considered an optimization candidate. It's talking about this code. That's because this function is declared here, but it is defined in a separate source file. So the compiler has no idea what's going to happen to A and B, and it is unable to use vector notation for that. So let me start playing with this and to see what can be vectorized or not. First, let me see the effect of this pragma. Pragma no vector. So I will disable vectorization of this loop. And to see the result, I will go and type make, go back, and reread the vectorization report. Right, so now line 33, the loop was not vectorized because no vector directive was used. That's what I wanted to see. Now let me see what happens if the loop becomes slightly more complex. So this is trivial to vectorize. I load 16 values of B, I load 16 values of A, add them together, and write the result out. By the way, to see what exactly the compiler did, maybe I could produce the assembly code, the assembly listing for you. I will show it once to explain why I'm not going to show it in the future. So I will compile with the argument capital S, and then when I go to vectorization.o, it will actually be the assembly listing. So if I try to search for line 33, you can see that the compiler does vector loads, and actually it unrolled the loop. See, it does 4 vector loads, then it does 4 vector additions, and then it does 4 vector stores, and it checks if the loop has finished and basically loops over. But I think actually in this case this was relatively simple, but let's see what happens if instead of declaring B like this, I will declare B like that. Double pointer B equals. So I am doing memory allocation on the heap. I have to allocate this many bytes. And in Fortran, this is an equivalent of using an allocatable array. So here, the compiler no longer knows the loop length, so it is unable to run this expression. I have to specify the loop bounds. So when I recompile, let me go back to the assembly listing, and actually, let me rerun this command, which compiles it with the argument -s and reread vectorization.o. So now let me search for line 34. You can see that I have some additional instructions, and I think I should have another code path somewhere here. Now, how about line 33? I was expecting the compiler to implement different code paths. It didn't do that. How about I tell it that I declare n not as a constant but as some number that comes from somewhere else. Well, this is not a good code. It actually won't run, but it will compile. Or maybe I will do that. So I pretend that I pass the value of n from the command line. So this is what I need to add to make it work. Now let's see what the compiler did. So these additional instructions, I think, deal with the situation that B may not be aligned on a good boundary. And let's see what happens when I also make n a runtime constant. So let me search for line 34. So I still have the same story. And now I keep searching and see I now jump to a different piece of code that also deals with line 32. And I have scalar instructions here. And the compiler said that this is, well, probability 10%. Then I have some vector instructions, and going down the code, I see a lot more code corresponding to line 34. So this is where the compiler probably implemented a remainder loop to deal with a situation where n is not a multiple of 16. So let me try again to confuse the compiler. Let's try to do this. So 1 is going to be a constant across different vector lanes. So when I compile, let's see if the code still vectorizes. And I will go back to vectorization O opt report and look at line 33. Actually, it says that in line 33 loop was vectorized, and you can see that it prints, see, the remainder loop was vectorized, still applying to this code. And then non-scalar, non-vector remainder is also possible. So let's see what happens if I have something complex like transcendental functions. Is it going to vectorize? When I compile, the compiler will actually complain it doesn't know sqrt until I include the header file for the Intel Math library. Now it compiled, and let's see if this was vectorized. So I want line 34. Yeah, loop was vectorized, so the compiler knows how to do that. What if I have more than one line in this code? Suppose I have something like this. This is not a meaningful calculation. I just want to see if I can make my code more complex and still have it vectorized. Still vectorized. If you want to take a look at what happens in the assembly, we will produce the assembly again and search for lines 35. So line, now the code is really getting complicated. See, I have different branches depending on runtime situation for loop lengths. I have a square root called as a vector instruction. Good news. I have these uh, instructions dealing with weird alignment situations. Then I have another square root. For some reason this is a scalar square root, so maybe this is the remainder loop. But you can see that the code becomes pretty difficult, and the compiler is trying hard to do appropriate amount of unrolling. See, it unrolled by 4 vector iterations, and then it's dealing with these different situations. So the code is now pretty long, and I wouldn't want probably to write it myself. The compiler handled it pretty well. Now let's see something that is not going to vectorize. If I want to put something like this here, so I included a third array, and I will use it as in this expression to get indirect array references. Recompile, go back to the vectorization report, and look for line 35. In line 35, yeah, loop was vectorized is, I think, misleading. So let's see what happened here. Maybe this is because the compiler knows at runtime what's happening. So how about I initialize it like this. Yes, so now the compiler says loop was not vectorized, vectorization is possible but seems inefficient. That's because, well, it actually knows at compile time what this pattern of memory access is like, so it thought it was not efficient. I can use pragma vector always to tell it to vectorize even if it seems inefficient, even though sometimes this is not necessary because it will not lead to better performance, but I just wanted to illustrate this pragma. Oh, you know what? I apologize. I was looking at the wrong loop. No, I'm sorry. I'm confused. Yes, so this loop is still vectorized. This surprises me, but let's let it be. Maybe if this is in the left-hand side, this will be difficult. Yes, if it's in the left-hand side, that will be difficult because yeah, so now the loop was not vectorized, and the compiler recommends to use level 5 of verbosity for enough details. And there is the problem that there is flow dependence between line 39 and 39. Basically, in this line, I have a problem. So why did it vectorize with C of I in the right-hand side but not in the left-hand side? Actually, it would not vectorize if I have it here. This is because A is read-only and B is actually modifiable. So the compiler detects situations like that. So let me go back. Yes, so the loop is still not vectorized, and that's why. The compiler doesn't know what is happening here, and there may be two situations. One situation may be like that. something of this sort. This is easy to vectorize. There may be a situation of this sort. So now I have a stride. Now I have a gather operation. This actually should vectorize. Line 37, yes, loop was vectorized. And to see what is happening, I can edit my make file. And in the make file, I can set qopt report equals 5 for the highest verbosity level. So I have to use make b to recompile because I didn't change the source code. And let me go back and search for line 37. A lot of interesting things happening. The compiler is implementing multi-versioning depending on runtime situations for alignment. For example, A may be aligned, B may be unaligned. And then it has unit stride loads and stores, and I'm looking for a gather operation. Looks like no mentioning of a gather operation. Oh yes, sorry. There you go. Strided loads. This applies to loading every other element of vector B. Now, if I look at the vectorization report for the mic architecture, the file is called vectorization.omicOptReport. I should see something different. Well, it actually still says masked strided loads. So the compiler can vectorize this. If this is what's happening behind C of I, it would work. What about a situation like this? So this is what you could get in a stencil operation, something like that. If you're doing a stencil, I don't know, image blurring, you may use this element and the next element. Is this going to vectorize? By the way, this is very non-trivial to vectorize in a GPU, but it will vectorize on Xeon Phi and on Xeon. So you can see that still loop was vectorized, even though I'm using this element and the next element. It is still safe to take 16 elements of B, load them into vector register, perform the operation, and then store them into vector register at PI. But that is not going to vectorize. So let me illustrate the difference. I used to have this. Now, instead of I plus 1, I will use I minus 1. And this introduces vector dependence. I cannot compute B of I before I know B of I minus 1. And now if I search for line 38, is it? Oh, it's actually 37. Loop was not vectorized. Vector dependence prevents vectorization, and this is the dependence issue. Let me do one more experiment with this loop to see if the compiler can deal with branches. And branches I will do like that. For example, if C of I equals 3, then do that. Compiling. And I think it will be informative to compare the host vectorization report to the Xeon Phi vectorization report. So look for line 37. Yeah, I'm sorry. There we go. Line 37, the compiler says loop was vectorized, and it has unit stride loads, and it's talking about masked unit stride loads. Now let's look at the vectorization report for the Xeon Phi architecture. And it shows, yeah, it's also talking about masked operations. So what's going to happen at runtime is, I believe usually the compiler calculates this expression for all vector lanes, and then it uses this mask to either write or preserve some elements on output. So this is where vector divergence, where what you would call thread divergence on a GPU could occur. But in the case of Xeon Phi, well, you'll just calculate the entire code. Now, it's interesting that if you take this branch very, very rarely, the compiler will actually implement all this calculation, even though the branch is taken very, very rarely. So sometimes using pragma no vector can be good for performance, because if this branch is taken once out of 1,000 iterations, it's cheaper to do this with scalars than with vectors. All right, I think I squeezed everything I could out of this little loop, and I hope it was informative. So the compiler can vectorize simple loops. It can vectorize loops when it really doesn't know the loop count, because it can implement a remainder loop. It can deal with different alignment situations at runtime. The body of the loop can be complex. You can have forward references. You can have some indirect accesses, such as this one, if as long as these indirect accesses do not cause real vector dependence. You can have branches in vector loops, and you can have constants across vector lanes. You can have transcendental operations. You can even do some type conversion if you want something like this. Well, actually, no. Let's not. Well, why not? Something with a type conversion will still vectorize. So I hope that I convinced you that the automatic vectorization functionality is very powerful. So with this type conversion from integer to double, I still have the loop vectorized. Now let's focus on other opportunities for expressing vectorization. I'm sorry. Let's focus on other methods of expressing opportunities for automatic vectorization. And let me now go to loop number 44. So loop number 44, I will go to the vectorization report and just search for parentheses 44. The compiler says loop was not vectorized, and then it says loops with early exits cannot be vectorized. I think that the compiler is a little confused, but we can fix that. So, no, the compiler is not confused. So what, let's see. I know exactly what's happening. I'm trying to think in which order to illustrate how to fix that. So I have this function that calls a plus b essentially, but the compiler has no idea what's happening inside this function, because the body of this function is in a different source file, worker.cc. This is that function. To tell the compiler that this function may be vectorized, let me use the Intel notation to declare this function as SIMD enabled. And before I actually do that, let's look at the vectorization report for worker.cc. So I think I have too much information. Let me go to the make file, reset vectorization here, verbosity to 0, and then revisit the vectorization report for worker.cc. Okay, this is easier to read. I'm interested in this function, line 13. And the compiler really doesn't have much to say in the way of optimization here. So at this point, I will declare this function as cmd enabled. And I will compile it. Now let's see what the compiler has to say. Now there's a lot of information about my scalar add. I have one implementation of my scalar add labeled as n2vvs, and this function was vectorized. This is a new message. Now I have n2vv, and then m2vvs, and also probably m2vv. Here's what's happening. The compiler is prepared that for the situation where this function is used in a data parallel loop. If it is used in a data parallel loop, the object file will now contain an implementation of a non-masked vector version of this function. It will also contain a scalar non-masked version of this function. And then the compiler also implemented a masked version of this function, where this function is called not just from a loop, but also from a loop with branches. And also, here's an implementation with masking, but without vector operations. So actually, let me do a little experiment. So now I compile this function as, yeah, I want to prove to you that the object file is large. How can I do this? I think I have to go to the make file, add CPU objects, and this way the make file will not delete the object file. So I will comment this out. So now I have a plain function. Let's compile and look at the size of worker.o. So worker.o is 1.8 kilobytes in size. To make it more, well, yeah, that's fine. And now I will go back and comment this, remove the comment. So now this is a cmd enabled function. So when I compile, the object file becomes bigger because now I have many implementations of these functions in the object file. Now what about the loop that uses this function? What happened to it? I go to vectorization.o, .opt report, and look for loop in line 44. Actually, let me recompile everything. Make b. Vectorization O opt report. Yeah. I'm interested in loop in line 44, so I will just search for 44. And the compiler says loop with function call not considered an optimization candidate. But wait, didn't I tell you that this is a cmd enabled function? Well, I did, but I did it inside of the worker.cc file. When the compiler compiles vectorization.cc, it has no idea of what's happening inside of worker. And this is the signature that it reads. And the signature says nothing about cmd enabledness. So I will add the cmd enabledness flag also in the declaration of this function. So now I will compile. And actually I need vectorization optimization report. Now let's look at line 44. It is still not vectorized, but the message has changed. The compiler says loop with early exits cannot be vectorized unless it meets search loop idiom criteria. I am not I do not design the Intel compiler, so I cannot really tell you what meeting search loop idiom criteria means, but I know as a programmer the problem that the compiler is dealing with. N, the upper loop bound, is not known at compilation time. It is only known at compile time. So when I reach here, the compiler, the runtime will know what the value of n is. And depending on the value of n, I may have to do different kinds of things with calling the vector versions of this function. To help the compiler, I will include a statement which gives it a hint. I really, really want to vectorize this loop. And then the compiler will put a little bit more elbow grease into it, and I hope the loop will now be vectorized. Unfortunately, not. Loops with early exits. Well, let's see what happens if I do it like this lab was designed. And set n to 100 to 10,000. Go back to the vectorization report. I know that this is vectorized, yes. So now loop in line 46 is vectorized, and it's a SIMD loop. I think it will actually be vectorized even without this. Yes, but I'm pretty sure that at some point in the past I saw this loop vectorized with n not being a compile time constant. Oh, by the way, to illustrate that having this makes the difference between vectorizing and not vectorizing, let me remove this, recompile and revisit. And now the loop is not vectorized. So let me bring it. Whoop, what happened? Oh, I closed my editor. It's unfortunate. Sorry about that. So now I will return this back in, rebuild, and reread the optimization report. So the loop was vectorized. So let me, if you don't mind, give me 10 seconds to think about what's happening here, and maybe I can figure out if we can do vectorization. Let me try one thing, and if this doesn't help, then I will give up. No, unfortunately this doesn't work, and I don't think that this is going to help either. What about ignore vector dependence? Looks like I have some homework, so I will report in next in the next. Yes, I will report in the next session what happened here. So we know that it vectorizes when n is a known compile time constant, like this, but it doesn't get vectorized when n is a runtime constant. Finally, I want to take a quick peek at what happens inside of this function. So here we are calling a function and we are passing to it two arrays by pointer. So the interesting things are now happening inside of worker.cc. So let me open the optimization report for it. And I'm interested in function in line 17. And loop is in line 18. So the compiler is saying a lot of interesting things. It says peeled, so it's implementing a peel loop. It says multi-versioned, so it's preparing for different alignment situations. And it's also talking about implementing an alignment loop and a remainder loop, and also a scalar remainder loop. And then we have version 2, where the loop was not vectorized because I have multi-versioning. So what is happening? As a programmer of this function, I expected that the user will always pass A and B, which are not aliased, meaning they point to different memory address regions. But it could be that B is offset from A by 1, and in this case I would have true vector dependence. The compiler is prepared to handle these situations, and let me first deal with the multi-versioning part. Multi-versioning I can remove by including pragma, ivdep, ignore vector dependence. When I compile, I should now see only one version, because with this pragma I made a promise to the compiler that loops are not aliased. So let me try to run this application. And I have to pass some argument, so this worked. But let me now try to do what the compiler doesn't expect me to do. And instead of calling this function, I will call say a of 1, address of a of 1, and then address of b of 0, of a of 0. Yeah, so in the right hand side, I will, in the first iteration, have how about just for protection do that? Well, is it going to work? I think so. So compile, the compiler suspects no wrongdoing on my part, but when I run the application, I expect to get a segmentation fault. Well, I didn't, I said it wrong. I should not expect a segmentation. Okay, I will show to you that I get incorrect results. This is what should happen. So let's see, how about this? I will set a of I equal to I. Actually, we'll run it right here. And then I will print the first few values of A. And then I will also set B of I to 0. So I will print a few values of A, but maybe just 16. So let's see what happens. First, I'm going to call this to test that everything works correctly. Yeah, so I added 0 to every element and it worked correctly. So now I will do that and I will remove this pragma. So what happened? What it did is it added the previous element to the next element. So 1 plus 0 is 1. Then I used to have 2. 2 plus 1 is 3. Then I used to have 3 here. 3 plus 3 is 6. I used to have 4 here. 4 plus 6 is 10. This is the correct result. This is, well, is it the Fibonacci numbers? I'm not sure, but sounds like it. So this is the correct result when I pass A1 and A0. Now let me use this. The loop was wonderfully vectorized in this case, as we saw, but when I run it, the results are different. The first 4 are actually correct, but starting from number 4, results are completely different. So the penalty for not really providing non-aliased arrays is that I get incorrect results, so I have to be careful with that. Instead of doing pragma IVDEP, I could achieve the same result with the restrict qualifier. And in the make file, I will have to include the argument -restrict. And as I noticed, as I explained in the lecture part, this promises to the compiler that no other pointer is pointing to the same memory address region. Let me check the vectorization report. And in line 19, oh, the wrong vectorization report. In line 19, I have loop was vectorized, and when I run the code, the results will still be, well, once again be incorrect. Well, because I promised one thing, but I delivered another thing. I promised that there is no pointer aliasing, but I actually fed to the function aliased pointers, so no surprise. Now let me revert this to the original situation where I get correct results and focus on a couple more messages in the vectorization report. Okay, so this is correct result. Okay, go back to the vectorization report. Loop in line 19, we used to have multiversioning. We removed multiversioning using pragma IVDEP. This makes the code supposedly faster in some cases, but less general. Specifically, it cannot handle cases where you actually have pointer aliasing. Now, I want to point out the other messages that we have here. One of the messages is peeled. Loop peeling means that the compiler is prepared to handle a situation where one or both of these arrays are not beginning on an aligned boundary, and then it will perform several iterations with scalars before it reaches an aligned boundary. We will talk about the performance impact of this in session number 6, but I want to illustrate how to tell the compiler to relax. If I can guarantee alignment, then I can do pragma vector aligned. And this hint promises to the compiler that all memory accesses in this loop are aligned. As you can see, peeling disappeared. Remainder is still here because n is not known at compile time. But if n was known at compile time, for example, I put it here as, well, 16. If n was known at compile time, then there would be no remainder loop. If n was known at compile time to be a non-multiple of 16, then there will be a peel loop. And finally, yeah, oh, I'm saying peel loop, I should have said remainder loop. Remainder loop. And finally, if again n is a runtime constant, then you will always have a remainder loop because the compiler must handle this array correctly. So yeah, I have a remainder loop. But let me go back to this vector aligned story. Vector aligned promises to the compiler that there is no need for a peel loop because A and B are aligned. When you make this promise, you have to deliver on it. To deliver on it, and we will discuss it in session 6, but I want to do a quick demonstration. To deliver on this promise, you have to make sure that your arrays are indeed aligned on a good boundary. If you're dealing with an array on the stack, you can add the attribute aligned and specify the alignment value in bytes. For Xeon Phi, the alignment value has to be 64 bytes. And if you're allocating an array on the heap, then you can do this. mmmalloc is a special allocator that guarantees alignment. So now, when I compile, I can never get the syntax right. Attribute aligned, I think like this. Oh, yes, I don't remember the syntax. I need to look it up. Okay. Yes, the syntax is different from what I remembered. So attribute, and then two opening parentheses, aligned, and then one more opening parenthesis, 64, and three closing parentheses. Not the best looking language construct, but it works. So the code compiles. When it runs, everything goes smoothly. But if so I had to do that because I promised to the compiler that there is no need for a peel loop because data are aligned. And finally, let me show you what happens if I don't deliver on this promise. For example, most likely when I use a simple usual allocator, yeah, on the host, I think in my architecture, I don't really require alignment. So let me edit the makefile so that on Xeon Phi I run with 10,000. So Xeon Phi will be picky about it. So on Xeon Phi I get error running this code because I promised alignment, but I did not deliver on it. If I instead deliver on the alignment, the code will run without an error. Or if I don't care what my alignment situation is, but I don't make these promises and the compiler implements a peel loop, then again the code still runs. So this is a preview of what we will be dealing with in session number 6 when we talk about the optimization of vectorized calculations. So today we talked about data parallelism and expressing data parallelism across vectors. I'm sorry, expressing today we started talking about parallelism. We discussed data parallelism, in other words, vectorization. Tomorrow we will talk about another form of parallelism, which is task parallelism, and we will talk about multi-threading. So today we learned to use multiple vector lanes inside of every core, and tomorrow, not tomorrow, on Monday, we will learn how to utilize multiple cores in a Xeon or a Xeon Phi coprocessors. That said, I'm ready to wrap up this presentation. If you joined us late, you can view it on the course page. And if you have any questions, I will stay online for a few minutes. Specifically, if you have a question about remote access, please ask it, and I will stay online a few minutes, and I will answer them in the questions window. Thank you very much for your attention. Have a great weekend, and we will meet again, same time on Monday. Bye.